Hopefully a quick video of the experiment I got going on interfacing a Raspberry Pi 3 to a Western Design Center W65C02S. I'm using the 3.3 volts from the Raspberry Pi to power up the breadboard. The shift registers, the 74HC165s, will operate from 2 to 6 volts, so 3.3 works. And the 6502, or the modern version of the 6502, will also operate at 3.3 volts at 8 megahertz. I'm going to be using a much slower clock speed than that. When the 6502 outputs an address, the Raspberry Pi will read it through these shift registers. The 6502 will actually be reading from or writing to a list in the Python software running on the Raspberry Pi. I don't have all of the pins on the microprocessor hooked up, but I do have obviously power, address, and data. There's also the clock signal, which will be generated from the Raspberry Pi, a reset, which can be monitored as well as controlled from the Raspberry Pi, a ready pin, and 2 interrupts, which I haven't done anything with yet, and also a read-write pin that will specify whether the microprocessor wants to read data or write data. So a quick rundown of the software. Import some modules here. Here we go down through and set up some of the pins. Here's the shift register pins. Here's the pins so far that are hooked up and set up to interface with the W65C02S. Come down through here and initialize Pygame. Here I've got a 64K list set up that the microprocessor can access when it wants to read or write. I've initially set it up with no-op instructions. So the whole list is filled with no-op instructions. And then I go back in and set FFFC, FFFD, and hex to hex 200. That's the reset vector. My first attempt at an assembly program, I'm not sure if my comments here are correct or not, but you know, it's not a very useful program, but at least it kind of demonstrates that that the process between the Raspberry Pi and the microprocessor is working. Basically, you know, taking the assembly, turning it into opcodes and memory locations, and putting it into writing it into the list, and then this is where it will execute. You know, like from up above here, you know, we said the reset vector was at hex 200. Well, in this memory list at hex 200 is our first load the accumulator opcode. So that's what we'll start. Here's some instructions printed out to the screen at first. You know, basic stuff like, you know, being able to press P to start, pause, resume the clock. You know, while pause, you could tap S to single step. While running, you can push the up and down arrow keys to change the speed of the clock a little bit, not too much. And of course, you can press escape or Q to quit. Here's an get address function. So you know, we'll shift in the address from the microprocessor to the Raspberry Pi. Then we get into the main loop where we process the events, you know, monitor and react to the keyboard key presses. You know, for timing here, the speed of the clock, we set it high. Would draw to the Pygame screen just a rectangle to indicate that the clock is at the high state. And then we get the address. We react whether we want to read or write. We might, you know, we get the input from that pin, and then we print some information out to the Python shell window. The clock goes low. That's timed out, and we go back up to the top part of the loop and do it all over again. So let's get it set up to run. We've got our little bit of a help screen here. I'll bring the little tiny Pygame window up into view. And right now we started out paused, so we can single step through initially. So that was our first step through. We go through a 7-step reset sequence. So as we can see that the reset pin here is in the high state. The ready pin's in the high state. The read-write pin is in the high state, which means it wants to read. And then here we've got address and data information. But like I said, we're just single stepping through a reset sequence. So there's step 2, 3, step 4, 5, 6, and 7. So that should be the end of the reset sequence, and then we should start going into the reset vector, which we set in the list in the Python software. So here's that FFFC with the data of 00, 0, and then FFFD with the data, you know, hex value 2. So that's going to be our address where we're going to start running our program. So if we single step that, you can see that we did go to that address, and there's our first load A, you know, an opcode there of A9. And there's our data at the next address. And there's our next command, which, if I bring that up, is a transfer from the accumulator to the X register. Let's go back to the program. Single step it through. Here it is, CA, which is we're going to subtract 1 from the X register, from the value that was just put into the X register, which was that hex 22. Takes a couple of cycles. And here we're going to store the X register. A couple of cycles there, and then here we're starting to get the location in memory, or in this case, you know, a location in the list that we're using for memory, where we're going to store that new value, which should be 21. So here you can see it's at hex 310, and there it is. There's our data, and there's our read-write pin, which says that it wants to write that value, the low indicating that it wants to write the value, and that was the value at our address 310 that we specified. And here I've got a no-op instruction, and 4C is going to be a jump, a couple of clock cycles it takes, and then we are going to we're going to go back to memory address, or in the list address, at 207, which if we come back over here, 207 is going to jump back up where our no-op is, and then it will fall back through and keep jump back up to the no-op and fall back through. So it's going to keep looping right there. We can unpause and put single stepping and let it run through, and as you can see, it's a pretty slow clock signal right now. We can increase the speed by tapping the up arrow key. And we can pause. And then if we want to, we can quit. And then it cleans up and ends the program. And just to double check, I've added a line here to print out that hex value that we're going to write to the list at the end of the program. So let's run that and see how it goes. So I'm going to bring this up into view here, and I'm just going to let this run. So there's where we wrote the value, and we're starting to loop. So I will pause and quit, and there it is. There's our 21. So the hex value 21 was written to that address 310, and after we quit the program, it printed 310 hex 310 from the list, and it agrees. So it did write that value to the list.